I want you to consider this problem here that we've got, okay? And we're going to look at an alternative way at resolving forces, okay? So we have, for the past 2 weeks now, been looking at forces in the vertical. Well, we started in one dimension where we looked only at forces in the horizontal, and then we looked at forces in the vertical. And last week, Friday, we looked at when we combine these two, right? When we actually look at forces in both directions, right? We can resolve forces. We can split them up into two separate components, and we can resolve the horizontal and the vertical components, right? And at the moment, we've only been focusing on forces in equilibrium, right? And if we have forces in equilibrium, that means the horizontal and the vertical components are equal, right? There must be equal forces in the opposite directions in order for them to create a net force of 0, okay? So if we consider this problem that we have here, right, we have two unknown forces. We have unknown force R, we have unknown force T, and we have unknown force, well, we actually have a known downward force due to the weight of this object of 10 newtons, okay? So how we would have done this based on what we've learned last week is we need to separate both of these unknowns into their two components. So here I have component R, okay? And you can see all I've done is I've just separated into its horizontal and vertical components, right? Remember, they are always perpendicular to each other. And the unknown component is the hypotenuse. So here's my R horizontal component, and here's my R vertical component. Okay? I've used the fact that because we are working with parallel lines, that this angle up here is also 65 degrees, right? To show you that, I can quickly, right, if I just create a quick horizontal line here, you can see that these two angles are alternate angles, and so they are the same. Okay. Stop me if I'm making no sense and you want me to explain something again, all right? Now, using our good old trigonometry, I can solve for the horizontal component and the vertical component. And that gives me, this is my horizontal component, R cos 65, and R sine 65 as my vertical and horizontal components, okay? And I can do exactly the same thing for T, all right? So here's component T. All I've done is I've kind of just pulled it off to the side, and I've separated it into its horizontal and vertical components, okay? So I've done that in the background, obviously, to save time, because if we had to sit and do that together, that would take a long time. However, the next step we can sit and do together, right? Zara, what can you tell me about the two horizontal components, Rx and Tx? What can you tell me about those two components? I want you to think about the direction that they're acting in and the fact that we have this thing in equilibrium.
They add up to 0.
They add up to 0, okay? And if they add up to 0, that must mean that they're actually equal to each other, all right? If you think about these two forces, they're acting in opposite direction. One is positive and one is negative. I'm going to give you a really silly example off to the side here. One is positive, one is negative, right? And the way we write negative forces is with a minus. And quite correctly, you've said they add up to 0, right? And so if I just move the other one to the other side, you can see that in order for there to be equilibrium, these two forces must be equal to each other, okay? So what I'm going to do is I'm going to make the two horizontal forces equal to each other. The horizontal forces, right, that's why I've labeled them X and Y, because we know X is normally horizontal and Y is normally vertical, right? So name your forces so that you don't lose track of them. So R of X is basically R cos 65, and that's equal to the horizontal component of T, right, which is T cos of 25. So there's my 1, right? I've got two unknowns. So in my head, I'm thinking I'm probably going to have to solve simultaneous equations, okay? Let's think about the vertical components now, all right? We've got 3 vertical components, okay? We've also got the vertical component of that 10 newtons going down. And again, the vertical components, the ones in opposite directions, must be equal to each other, right? So the 2 forces pulling up in this direction are the ones that come from the components of R and T. So that's going to be these 2 guys here. You can see they are acting up, right? If you have a look at them in my diagram. So if we add these 2 forces together, so if we add R sine 65 and T sine 25, they must both be equal to the force acting in the opposite direction, which happens to be this 10 newtons over here. So this must be equal to 10 newtons. So there are your 2 simultaneous equations, and you could, in theory, you could solve now for R and T if you wanted to. Okay? Now, look at those 2 equations and please tell me you think that those don't look messy. Okay? So we've got 2 unknown forces. We're trying to create 2 simultaneous equations, and so things get rather messy. Okay? Now, Kiana, what do you notice about that 10 newtons? What was the nice thing about that 10 newtons that you can, maybe you spotted something interesting about it? Have a look at the other 2 forces and have a look at the 10 newtons. What can you tell me that's different about the 10 newtons? Anybody want to venture a guess? Well, what I want you to have a look at is look and tell me, do you see any component forces of the 10 newtons, right? This force here of 10 newtons, it has no component forces, all right? So a very important thing that we need to learn is that if we have a force acting in a line of action, right? The line of action is quite simply what we decide to be north or up and down and left and right. Okay? A force has no component perpendicular to its line of action, right? So to give you an example, I'm just going to quickly draw a dotted line for you. Here's a line of action. I'm saying the line of action is left to right. Okay. If I have a force acting perpendicular to that direction, right, whatever this force is, when we are resolving forces, this force will have no component in the horizontal direction. Okay. And we can do the same thing for the vertical. So if we have a vertical line as the force of action, or the line of action, sorry, and we have a component perpendicular to it, there will be no force in the vertical direction. Right? Does that make sense to everybody? Right? If you consider how we've been analyzing forces as up and down and left and right, when we've resolved them, we've split them up into their up and down and left and right, right? And we consider them separately. We consider the vertical components separately, and we consider the horizontal components separately. So when we're looking at vertical components, there are no horizontal components. Right? Everybody good with that? Yay, nay? Makes sense?
Yep.
Yeah, you got component up and down, left and right. There is no component in the perpendicular direction, okay? Which is a really nice bit of information. So let's go back to this problem here that we just did before, all right? And let's use the fact that why do we have to have up and down and left and right as our line of action, okay? And the simple thing is because it's convenient. But sometimes it's not convenient. So in our case, in this example, it's actually not convenient to have R and T off at some angle. And so what we're going to do is we're going to change the line of angle. Now, obviously, in reality, you know, you can't do this on your question paper by just rotating, but I'm going to rotate this now. And I'm going to rotate it so that my unknown forces are now vertical and horizontal. So Dominic, does force T have a horizontal component anymore?
No, it doesn't. Not anymore.
Okay, what about force R? Does it have a vertical component anymore?
No.
No, because we've changed the line of action, right? We have eliminated these forces, right? And so we don't have to consider them anymore. So now the only force that needs to be resolved is that 10 newtons, right? And the nice thing is, if you go back to our first look, we had to resolve two forces here. We had to split two forces up into separate components with two unknowns, right? And we had to now solve simultaneous for these two unknowns, which can be very messy, okay? Now, just by simply rotating the image in our mind, obviously in reality, you can't rotate the image like this. You just need to change the line of action, right? So I've changed the line of action. I've made T and R vertical and horizontal. And all I need to do now is consider this 10 newtons. And that's what I've done off to the side here. Now split the 10 newtons off into its two components. And now I have one for the horizontal and one for the vertical, right? So Zara, what can you tell me about force R and the horizontal component of that 10 newtons? This force here and this force here. If this object...
They would be equal to each other?
Absolutely. Okay, they are equal to each other. Okay, and so we can solve for R straight away without having to go through the process of trying to solve some simultaneous equations. We would have to solve these equations simultaneously in order to solve for R and T. But by changing the line of action, right, and eliminating either the vertical or the horizontal component by making R and T the new lines of action, we are able to solve much more quickly and more accurately. Okay? And we can do exactly the same for the vertical component. So the vertical component T over here and the vertical component T over there, they must also be equal to each other. And that brings us to the whole point of today's topic, right? And that's that the component of force F, right? I'll explain this, but I'm going to read it first, right? Parallel to a given direction P can be found by, well, that force cos of the angle, where the angle between the force and direction P. So I want you to think of force F over here, similar to that 10 newtons that we just split up, okay? If we change the line of action, if you'll notice my line of action is my purple line. If we change the line of angle, or the line of action, we need to know the angle that the new angle creates. But the important thing I want you to notice is that still creates a 90-degree triangle, and we can still separate these into two components, right? They just won't be in your eyes vertical and horizontal, right? But they will be perpendicular and parallel to the new line of action, okay? And when you think of a line of action, this is all I want you to imagine in your mind, okay? This is what we've been considering our lines of action. And what we're saying is, well, we don't always have to have them horizontal and vertical. Why don't we just rotate them, right, depending on the forces that we are given, right? So if my lines of actions were like this, we would just resolve forces in this direction with forces in that direction, and forces in that direction with forces in that direction, right? But we're still resolving forces only in two directions, and these two directions are always going to be perpendicular to each other. Okay, before I move on, is everybody happy with that? Do you understand what I've just explained?
Yes.
Yeah.
Okay, well, let's move on to some examples and let's see how this helps us in some problems. Okay, so here we have a boat, right? The boat's obviously the point in the center, is held in equilibrium by forces, well, by three forces. Okay, there's a force of 10 newtons. There's a force F, right? And there's a force to the north of 20 newtons. Okay, and they want us to find the values of F and the values of theta, the angle indicated in the diagram. Now, if we have a look at this problem and we look at force F, if we have to resolve force F, we will need to split force F up into both a vertical and a horizontal component, right? Because at the moment, in our eyes, right, the lines of action are horizontal and vertical, right? And we've just seen at the moment that if we have this kind of scenario, we need to resolve two forces in order to solve for F. Okay? So what we're going to do is we're going to change the line of action, right? And usually what you do is you make the line of action parallel to the force that you're solving for. Because if you make it parallel to the force you're solving for, there is no perpendicular force anymore. So what that means is if I make the line of action in this direction like this, I'm just going to quickly change that to dashed. That's my new line of action, right? If that's my new line of action, the line perpendicular to this is the other line of action. And we can extend that over to the other side. So those are my two new lines of action. This now means what I can do is I can take my known forces, all right? I know what this 20 newtons is. I know the force and I know the 10 newtons here. I can split these two forces into their separate components because I know their values and I can use them to help me solve for the unknown forces. So now you would actually draw this on your diagram with dotted and dashed lines. I'm going to just pull them off to the side just to make things easier for you. So what I've done here, just to give you an idea, is I've taken this force over here and I've just moved it off to the side and I've straightened it so it looks more pretty. Okay, so this is the 20 newtons force over here. This angle inside here, all right, I don't know that angle yet. And so I'm just going to call it angle alpha. What can you tell me about angle alpha and theta at the moment, Kiana? What are they going to add up to eventually? if you have a look at the diagram that I've drawn.
Well, eventually it'll add up to 0.
Not quite. Have a look at angle theta. So this is going to be angle alpha on my diagram here. What are those two angles vertically opposite to?
So 80 degrees, we're going to make 80 degrees.
There we go. You see how those two angles are vertically opposite from each other. Okay? And we're going to use that obviously to help us later on. Now, I don't know what angle alpha is. That's fine. I'm sure somewhere we can figure out what it is. Let's quickly write down the vertical component of my force, right? This is going to be 20, right? It's opposite angle alpha, so it's going to be sine of angle alpha. And the bottom force is going to be 20 cos of angle alpha. I'm going to do exactly the same thing now for this force over here. So where did this guy come from? Well, this is this 10 newtons over here, which looked like this. And I've just pulled it off to the side with the power of magic. And we have this force here now, right? And I'm going to resolve these two forces as well. I'm going to split them up into their two different components. Toya, what is this angle inside here? This guy over here. What angle is this?
In which angle? So in the small triangle.
Yeah, what I know one of those angles. What is one of those angles? I'm going to quickly.
80.
Yeah, it's 80 degrees, all right? And I'm going to show you where that 80 degrees comes from because it doesn't just come magically. I'm going to draw a line. Let me see how parallel I can get that to, here we go, to my line of action. And you can see that this angle here and this angle here are just alternate angles between two parallel lines. So this angle inside here is 80 degrees.
Mm-hmm.
Now I can resolve my forces, okay? I've been told that this force is 10 newtons, so the hypotenuse is 10 newtons. So my vertical component, right? Vertical component is opposite that angle 80. So I know it's going to be sine, and it's going to be 10 sine of 80. The horizontal component, that's the adjacent side in the triangle, and that's going to be 10 cos of 80 degrees. Right, Dominic, how can I solve for angle alpha? I want you to have a look at all the angles that we have, all the forces that we have. I've actually drawn them in such a way that you can actually see all the forces, right? Look at the arrows. What can you tell me about the two vertical forces? Right? I've split my two known forces up into a vertical and a horizontal component. Right? Here's the one, and here's the other one. Have a look at the directions I've drawn my arrows in. They're acting in opposite directions. Okay? And these three forces in total are in equilibrium. That means that the two component forces that are acting in opposite directions, right, on the same line of action must be equal to each other.
Okay, so then it's just 2 sine alpha minus 10 sine 80, and then we solve for alpha.
Okay. Well, we can say 20 sine alpha minus 10 sine 80 is equal to 0. But using the fact that, you know, x minus y equal to 0 is just x equal to y. I can say that the vertical component going up 20 sine alpha must just be equal to the vertical component going down, which is 10 sine 80. And now I just have an unknown to solve for, right? I can punch 10 sine 80 into my calculator. It'll give me something. I can divide both sides by 20. Then I'll have sine alpha equal to something. And then I can use sine inverse to just find alpha for me. I'm going to save us the time. And this is 29.5 degrees.
Okay.
So now I have the size of angle alpha. Okay, now let us look at solving for F. Because I've chosen to make my line of action in the same direction as force F, I've eliminated all the vertical components out of the equation. Okay? So now what we need to do is we need to consider all the horizontal components. And I want you to see how I've drawn them in the diagrams. Right? Have a look at the horizontal components. Right? You can see that we have 3 horizontal components. This is the one that we're trying to solve. So Kiana, what equation of forces, net forces, can I make with those 3 forces? Remembering that if we add forces up in one direction, they must be equal to the forces acting in the opposite direction. So which 2 forces are acting in the same direction?
F and the 10 degrees.
Yeah, so F, the force that I'm trying to solve for, and this 10 cos 80, they are acting in the same direction. You can see even from my diagram, the arrows are pointing in the right to the left. Okay. The force acting in the opposite direction is that 20 cos alpha. And the nice thing is we kind of just worked out alpha in the previous step. It's 29.5. Well, this is a rounded figure, so you'd use the actual number saved in your calculator. And again, just doing some basic inputs on your calculator, you can solve for force F. As 15.7. Okay. We also had to work out angle alpha, or sorry, angle theta. But I said in the beginning, you can see that alpha plus theta is equal to 80 degrees. And that's because they are vertically opposite. And so you can solve for theta just by taking 80 minus alpha, and you will get 50.5 degrees. How are the brains? Are they good?
Brains are okay.
Okay, so I want to take this whole problem quickly, and I want to quickly show you. Actually, that's not going to work. Let me try from this side. The reality of what we've done, right, with my little diagrams on the left, is we've taken the whole picture, and that's all we've done. Okay. We've made the components that we want into the vertical and horizontal components. And usually the components that you want to use as your line of action are the ones that are unknown, right? Because it eliminates having to have 2 equations with unknowns in them, right? When I make force F the horizontal component, it doesn't have a vertical component anymore, all right? Right.